in Tokyo, in the very high building. I suddenly felt the movement of building. And getting increased, moving larger and larger. So I thought this is of course earthquake, and bigger one.
津波警報が出ました。津波警報が出ました。今すぐに
Major earthquake hitting Japan on Friday afternoon. Japan's meteorological agency says.
I saw the news and I saw the huge tsunami and I was very surprised and start thinking what we should do as scientists. I am interested in Earth, and when I was a kid, I saw the world of plate tectonics. And at that time, plate tectonics is kind of new concept. And also, I like to see the map of the ocean and the continent. I don't know why, but still I like map very much. My goal is to understand the subduction process. So to do that, we have to choose the correct tool in the correct timing. Right now, Chikyu is one of the best tools to get the sample from the fault.
When the helicopter came in, I had a window seat that was on the side that we could see the Chikyu. And it almost brought tears to my eyes. It was like coming back home. I was a PhD student. I had been doing fieldwork on shore in northern Japan for several years before the earthquake. I spent a lot of times in the towns along the coast and then saw the news and the devastation. In places that I had been with people that had helped me and hosted me, that's when it hit home. Why the work I do matters and how I could try and help give back to the people who were impacted by this earthquake by trying to understand the science behind it and trying to improve our understanding and our hazard mitigation for this.
Adding some interpretation and we can kind of get it out there as a publication.
The Tohoku earthquake was back in 2011, and at that time I was working as a postdoc at the University of California in Santa Cruz. And I'm a geologist, I look at rocks, but I was working in the seismology group there. And so I was working with a bunch of people who study earthquakes. The earthquake happened, and then early in the morning, some of the scientists were already up at Santa Cruz processing the data. And I went into work in the morning and I was like, just news came in, there's a huge earthquake in Japan. It takes a while to kind of get a complete picture of what that meant.
The agency has issued a tsunami warning for Japan's Pacific coast.
The tsunami started near Japan and the wave crashed into Japan. It also went the other way. And so it went over the Pacific Ocean, past Hawaii, onto the west coast of North America and South America as well. But we're in California on the coast. And so I remember going out to the cliffs over the ocean and the ocean went out. That was the first time that I had ever seen anything like that. By the time it arrived in Santa Cruz, it was nothing like the tsunami in Japan. It was just one of those moments in my career where I was kind of in the middle of it. And so I thought, maybe I can try and help out here. Less than a year went by, and then I applied to go on the drilling expedition for JFAST. Spent 2 months at sea. I was involved in the ongoing research after the expedition as well. And then somehow along the line, we were having some meetings with some of the scientists from the JFAST expedition, and it just came up that we weren't quite satisfied that we'd answered the questions in the 2012 expedition. And so a group of us were kind of like, okay, well, maybe we can try and write a proposal to have another expedition and go back and see if we can fill in the gaps. We formed this organizational group called the Project Coordination Team. That was maybe in the spring of 2023 or in the summer that we kind of finalized the group with Marianne and Christine and Patrick.
I'm kind of a combination of a scientist, a little bit of an engineer. I work in an engineering college at Cornell University. So I do things a lot with fluids, hydrology, things with heat, but also those things and how they relate to rock mechanics and geomechanics. So together, those kind of different fields, I'm all within there. I'm very much learned from ocean drilling, all of the bits and bobs that go into these things. Learned a lot about being creative and building an observatory, taking things off the shelf, building things to be able to do this types of science that we do.
I'm Julius, and again, it is difficult to predict the earthquake, but on the other hand, we can sometimes answer to what's happened, what is the mechanism of the large shallow slip. And personally, I'd like to examine the healing state using the fault zone material. Last time, I performed a high-velocity evolution experiment to understand why large slip occurred during Tohoku earthquake. This time, I would like to perform a so-called slide-hold slide test to examine relationship between changing friction strength against hold time, equivalent to the healing time. If we can establish such kind of equation, then we can input 30 years later or 100 years, and then I'd like to know the timing of the next huge earthquake.
I didn't really like mathematics, but I was really keen on physics. So everything that touched experience, try to understand why temperature changes, why things changes. I was always wondering, and I wanted to see and understand what was going on. And I was on this boat on the very first expedition, and I arrived and I barely knew nothing about subduction zone. I mean, I knew the name, but I knew nothing about it. And I was sitting next to somebody, quite experienced researcher, and I told him, yeah, sorry, but I know nothing about subduction zone. Can you just tell me what to read or something like that? And we had a lot of time in front of us. And he was like, yeah, sure, so you should read this. And this is when I realized that I was reading a book, like one of the Bible of the subduction zone, that was actually written by Casey Moore, the guy that I was talking to. And so this is how I started. Like, I was like, wow, that's super cool. Oh, this it works. Okay, right. And then I get into it, and I never went away from this.
What the engineers and the drillers are doing here is really at the edge of what's possible with the drill ship. And this ship, I think, is the only one in the world, for scientific drilling certainly, but maybe generally, that's able to drill in these water depths. So 7 kilometers of ocean is between us and the seafloor. It's astonishing how far it is and what they're able to do.
Basically, when we arrive at a site, we are blind. We don't see what's inside the rocks. So what we're gonna do is we're gonna drill a hole, and we're gonna measure, while we are drilling, a lot of parameters of the rocks. So this tool is called the microscope. It's a tool to measure the resistivity of the formation. What is that? It does is that we send an electrical current into the formation, and we look at how the rocks respond to that electrical current. It will tell us things about lithology, so the rocks that we can find inside the formation, but also if there is a lot of water inside it, if there is fracture. But the best with that tool is that we can also see an images of the borehole wall. So while we are drilling, we are basically rotating the tool. And on the tool, you have sensor here, here, here. And those sensors, while you are rotating, they are taking an image of the borehole wall. And so in real time, we can actually see what is inside the rocks. Above that tool, we have the sonic scope. This one sends an acoustic wave, so it's like a sound. It sends a sound in the formation. We look at, again, if it's fracture, if it's a hard rock or soft rock, also if it's damaged or not, which is very important for us, especially when we cross the fault zone. Below those tools, we have another tool right here. That's the yellow one that you see. And attached to that, we have the bit, the pieces that will break the rocks as we go down. The logging while drilling will provide information about the state of stress, for instance. This is very important for us to understand if we are at the moment in a new step of the seismic cycle and if we are adding more stress on the rocks than before. So this is one of the things that we are looking for. But the way science works is that you propose an idea based on the data and the observation that you've made. If you have only one piece of the puzzle, it's a very good thing to go and talk to other people, and then mixing all that together comes out with interpretation that works for everyone.
Okie dokie, we are going to spot.
You have to imagine that you have up to 8 kilometers of pipe and that we are reaching into rocks that are under massive pressure. And you're drilling, but the wall is 7 kilometers away from you. And you're on a boat, and you can only change the velocity of the drill, put more weight on it. They are feeling the rocks. And when you start to talk with drillers and you say, hey, I've seen on the data that something has changed. Say, yeah, I felt it.
On this type of expedition, we're doing many different things, but for me, the coring side of things is the most exciting. We have an idea about what's down there and what we should be getting back in any core, but when they come up on the deck and they're unpacked from the core barrel, you never quite know. Here, by accessing the fault, we are hoping to be able to evaluate what does it take to move one part of the Earth's crust past another part of the Earth's crust. And what I mean by that is like how much you have to push it, what's the stress acting on the rock and acting on the fault, and how much does it take to be able to get the earthquake to move this enormous distance.
So we're here right on top of the fault that slipped by many tens of meters during the Tohoku earthquake and displaced the seafloor and generated the giant tsunami that devastated the coast of Japan. And we are doing this in 2 locations. One location is on the rocks and the sediments that overlie the Pacific plate before they kind of enter the damage zone or the collision zone where the 2 plates meet, so that we know what they look like before anything happens. And then our second site is going to be across that fault zone, across that damage zone where the 2 plates meet, so that we can kind of see the before and after. I will be a very happy co-chief if we are able to recover rocks from the fault zone, from the plate boundary itself. It's a good part. If we can get all of the rock units at this site across the fault and a site on the incoming plate, this will be the first time that we have both the reference, undeformed, and the deformed site within close proximity to one another. This is essential for us understanding kind of the earthquake processes here.
Other updates or questions?
Once a core arrives on the ship, a certain number of things happen to it to prepare it for analysis. we have a team of people who then take turns to do lots of different kinds of measurements on it. Other people at the same time are looking and trying to understand what the materials are made of, how they're arranged with respect to each other, have they been mixed up by all the tectonic activity here in some way. And then there's other people who are trying to understand these complicated rocks. Where have they come from? What are they made of? Like, do we understand them here where they are today compared to their lifetime where they were formed previously? So these cores have come up from some hundreds of meters below seafloor. They've been assessed for various physical properties, and we've looked at them and tried to figure out what they're made of and where there are variations in them. Scientists are now taking samples so that they can take little pieces of this and take them back to their labs back home and do different kinds of analyses that we can't do on board the ship. So this is for their personal research after the expedition.
One of the magical things about ocean drilling and about the Chik-U is that you become like a family here, and everyone's working together. Having conversation all the time. You can't get them to stop talking about science and about fun and life. That is what makes me happy here.
I am the probably oldest person in the scientific team, and I'm very much enjoying watching the people, young people discussing, and the co-chief leading the discussion and so on. So I'm very happy to see that. The team consists of the very wide generation of the very wide background of people, and they discuss very actively and try to understand result of this expedition and try to understand earthquake mechanism. This is very nice to me. For example, now we have 6 co-chiefs, and 5 co-chiefs among them, they were on board of Chik-U vessel during the JFAST experiment as young scientist or student. Now they grew up the co-chief. This is a very good kind of cycle to educate a new generation.
As a co-chief, but also as a scientist, I always encourage people to communicate. The magic, something which is probably much easier on the boat because you're not PhD student in front of a big professor. You're basically living in the same space 24/7. The frontier that you have between PhD students and professor, for instance, start to disappear.
Good thing for ocean drilling, they are sending many expertise, like structural geology, sedimentologist, geochemist. And for example, so we identified a fault here based on changing structure or changing lithology or changing chemistry. We discuss in front of the core. But such exciting discussion is very good.
So I think earth scientists are pretty remarkable, creative thinkers. They can see a thin section, a little tiny microscopic image of something, and they can think about the whole system. But it's really complex. And that's why we're back here after JFAST. We want to get more understanding of this small little site where there's a lot of slip. What does it really look like? A little bit more in 3D.
And for me, this was really the trigger that sort of got me thinking about this.
We recovered the décollage. We did it, which was very exciting to see that come on deck. And in fact, we were able to make 2 passes through it. And then we were also able to recover the complete stratigraphic section on the incoming plate, all the sediments on the Pacific plate. And right now we're gearing up towards trying to go for the basalts of the incoming plate and at 2 sites. So we're on track.
I've never seen anything like this. This is what we came for, and it's been worth the wait. You know, we were hoping to get the core back with some basalt on it, but then to have all this extra stuff going on, this is what we were waiting for. The drilling has been really amazing, and the core recovery has been fantastic, and it's a really big advance on 12 years ago. I think this is the first time, to my knowledge, that a fault anywhere has been re-investigated after a gap in time of 10 years or more, and this sort of equivalent set of measurements have been made. But come back again and we can add to the time series and really fill out that picture a lot more.
Once the coring operations are complete, the next phase is to install an observatory that's going to be measuring temperature and fluid flow across the prism and across the décollement. Both the logging and the coring data have been instrumental in helping us design that observatory. So the outline of the expedition was set up intentionally to have the logging while drilling first to give us that first look, and then the coring, and then use that to design our observatory.
What are the resistant forces that prevent earthquakes from getting very big, very large? One of the ways you can get to it is by measuring the frictional heat on a fault, measuring how much heat it produces. That's related to how much it slips and how much resistant stress was on it, how much breaks it had during rupture. To really get that answer, you had to drill across the fault after an earthquake. One of the main reasons why we built these types of systems after the big earthquake was to measure the little bit of increase in temperature across the fault that was caused by shearing by the earthquake itself, by the frictional resistance, just like moving your hands together creates heat. We were able to observe that with the JFAST data. One of the things we also saw was this hydrology. As earthquakes happen, aftershocks happen, fluids would go through. When fluid pressure builds up, it can cause the fault to get weaker, maybe cause it to deform, maybe slip a little bit easier. So our sensors have essentially a thermometer in them that is connected to a data logger. They're going to record every few seconds over time, potentially for years. They're all encased in titanium metal casings because of the huge pressures at 7-8 kilometers down underwater. They each have a battery, a type of lithium battery that can allow us to record for long periods of time, and then perhaps leave them there for many years to kind of see how the subduction zone evolves over the next 10 or 12 years. The first thing we do is we go down with a big tube. That essentially creates a hole that stays open. Then we go down with a drill bit. We drill down across the fault, 950 meters below the seafloor. We bring the drill bit back up. Now we build the observatory. The observatory is largely a steel tube that we're going to install down into that hole that we just drilled. Inside we have heavy weight at the end of a rope, and we've got our sensors attached to it. We lower it down to the seafloor, try to thread the needle one more time, detach, and we go away. Some of the things that we're trying to see with the observatory may be able to contribute and kind of make a more integrative understanding of the subduction zone.
Without any slips sense.
If we can understand what is the largest earthquake that could happen here and how often may it happen, then the people who plan the tsunami defenses might actually think about that when it comes to constructing those types of defenses.
It's not that we're just looking at rocks. These are rocks that have a meaning. They're associated with earthquakes and tsunami. The science that we learn from this hopefully can have an impact so that maybe we can mitigate that risk both here and in other places as well.
Around the Pacific Ring of Fire, there is many similar subduction zones. This is a very good example to understand the earthquake process. Looking at the Tohoku earthquake, tsunami is not only for Japan. The tsunami traveled to the other side of the Pacific. Understanding the earthquake around Japan also helped to the society all around the Pacific region.